BAIST Class 3410 Enterprise Switching, Lab 1. Switching environments that contain VLANs, trunks, ether channels, and the use of the spanning tree protocol. Due February 2nd, 2018. Prepared by Ryan Matthews, Colton Rumbolt, Stefan Susi, and Amika Uche. Prepared for John Berlowitz. Before we start going into our project, I believe it would be best to first describe quickly what switching is. Switching is a technology that will allow for specially made devices to receive, process, and forward data packets to different devices within a network. Network switching functions similar to how a post office operates, where packets containing enclosed information are received, their address destinations are read, and they are then sent off on the best path to reach their intended recipient. A network switch can process over hundreds and thousands of packets per second, but there are many different network protocols that can be incorporated into an existing switch network that will allow for the data traffic to be transmitted more efficiently and prevent the likelihood of data packet loss during transmission. For this lab project, our group has been given the task to create a basic switch network and to incorporate different networking protocols into the existing network infrastructure. In the first section of our video, we will be both identifying and demonstrating the purpose of the various switching protocols we have used throughout our switched network. Before discussing how all the different network protocols function within our network, we like to dedicate this first part of the section towards explaining how we set up our current network infrastructure. Our network follows the design standards of most network infrastructures, as it consists of a core, distribution, and access layer. We also have 4 machines operating on the same virtual LAN, a topic we will discuss later in this video, which we have called our engineering network for the purposes of this lab. This network will be made up of computers that will be used by the end users and shows that we are capable of pinging across our network. Our first test was to make sure that 2 devices connected to the same layer 2 switch were capable of pinging each other, which we did with Ryan and Stefan's VMs. Here we have a test performed by Ryan's VM, which has an IP address of 192.168.20.5, where it is trying to ping Stefan's VM of 192.168.20.6. It is this 192.168.20.x network which defines our engineering VLAN. Within our example, we saw Ryan's machine create an ICMP packet, send it to the layer 2 switch, where it then forwarded it to Stefan's VM. Our next network connectivity test will consist of Ryan's machine creating another ICMP packet and sending it across our network in order to reach Colton's VM connected to a different switch. Because both of these machines are on the same VLAN, their IPs will also consist on the same network. So Ryan will have to ping 192.168.20.7, and we can see that he is capable of pinging Colton's machine on the other side of the network. We also had an ITS virtual LAN that was used for us to remotely access any of our switches via SSH through a management machine, as well as played a role in allowing us to ping each switch to test its connectivity within the network for further troubleshooting if needed. We also want to focus on implementing some network redundancy into our network design. Each machine will be running on a fast Ethernet connection, which will have a transmission speed of around 100 megabits per second. This means that the layer 2 switches could have a maximum of 200 megabits per second of data coming into them at any one time, so we've decided to aggregate some of the switches' ports together to prevent any network bottlenecks from occurring. We used a 4-port link aggregation to the connections going to our core switch, so in the event that one of the distribution switches goes down, the remaining switch is still capable of sending data at a rate of 400 megabits per second to the core switch, which will account for each device within the network, meaning traffic going to the core switch will not face any form of reduced network transmission speeds. Now that we have finished explaining our network, we will now begin to discuss the different technologies and protocols we have incorporated into our network. In this part of the video, we will be discussing a topic that we had mentioned previously, that is the use of virtual LANs, or VLANs as we will now be referring to them. VLANs allow for us to specify a logical group that consists of end devices and places them on a virtualized network operating on top of physical hardware, so that we may better separate and manage the traffic we expect to see on the network. With VLANs, the broadcast domain for this virtual network is contained to only the devices that are a part of the VLAN that they have been assigned to. On screen, you will see an example of why someone may want to create separate VLANs on their network. They may want to create a separate VLAN to better manage their IP camera traffic or for their very own VoIP phones, as well as have its own VLAN for all the end device computers to communicate on and operate. For our lab, we created over 5 VLANs to function over our network. The first VLAN we created was VLAN 10, which we named the Internal Technical Services, or ITS, VLAN. This VLAN was given a network address of 192.168.10.0. This VLAN will be used to address all the networking devices within our network. Those switches do not need IP addresses to function. Applying these to the devices provides us with extra benefits such as testing network connectivity, which we saw earlier in the video, and provide us with an option to remotely manage our devices if needed. To connect the switch to VLAN 10 is fairly easy. If we show the running config for the switch, all we need to do is look into the interface for the VLAN we want to apply the IP address to. For VLAN 10, we just give it an address within the 192.168.10.0 network, and from there we can ping an SSH in the machine if needed. The next VLAN we created was VLAN 20, or as we called it, the engineering VLAN. This VLAN was given a network address of 192.168.20.0. This VLAN serves to provide network communications to all users who fall under the engineering department of an organization. If we needed to check that if a workstation was on VLAN 20, all we would need to do is go to layer 2 switch and run the command show VLAN brief and check which interfaces that they are connected to on the switch. In this case, we can see that ports 23 and 24 have been assigned to VLAN 20, meaning the workstations connected to those ports will be operating on the engineering VLAN. We also created VLAN 30 for the Human Resources Department. This VLAN uses the network address of 192.168.30.0. This VLAN is not currently in use on the network, but it is present for if we plan to add the additional department into our network. VLAN 40 was created for the Research and Development Department. This VLAN uses the network address of 192.168.40.0. Similar to VLAN 30, this VLAN is not currently used on the network as it is only configured on the switches for if we plan to incorporate a research and development department into our network sometime in the future. The last VLAN we configured was VLAN 666, in which we named our graveyard/dead VLAN. This VLAN does not have a network address as it is not responsible for any communication on the network. We configured this VLAN as a best practice measure as we want to place any switch ports that are currently not in use to a VLAN that cannot connect to anything. That way, if someone does gain access to a port that was not properly shut down, it cannot connect them to anything on the entire physical network. There is one VLAN on the switch that is present before we even configure it, and that is VLAN 1. By default, all traffic goes over VLAN 1. This can be a huge security vulnerability. Anyone who is capable of connecting to this VLAN will be able to see all the data communications. It is a best practice to disable VLAN 1 and to make sure that no interfaces are set up to use that VLAN. Looking back at our VLAN configurations on the layer 2 switch, we can see that VLANs 30 and 40 don't have any active interfaces applied to them, and that all the interfaces that aren't in use have been applied to VLAN 666. You may also notice that there aren't any interfaces applied to VLAN 1 as we are trying to avoid using that VLAN. The VLAN should be showing up as deactivated, but unfortunately we made some mistakes during our lab that still makes it show up that it is active. In the next part of the section, we will be going over the 802.1q trunking protocol. The 802.1q trunking protocol allows us to configure an interface that will be capable of carrying VLAN traffic to other switches on the network. This forms a point-to-point link between two network devices and allows for multiple VLANs to send their data over a single link. When packets are to be transferred over these links, they become tagged with a VLAN ID that corresponds to the VLAN that they are a part of. That ID is then read by the other switch to identify which of its ports is also a member of the same VLAN to send the data to, depending if it has the same VLAN database information as the sending switch. This way, we can have one VLAN spread across a network in multiple locations and make use of trunk links in order to send data packets between them. On our switches, there's two ways we can check our trunking information. We can check the running config and go through each interface to see which ones have the command switchport mode trunk enabled on them. Or there's another command we can enter, which is show interface trunking, and from there we'll get a detailed listing of all the ports that are listed in trunking mode. This also shows which VLANs are allowed over the trunk link as well. It is best practice to only allow the VLANs that you will be using across these trunk links, but in our video you can see that we did make a mistake and we did allow every VLAN to go across our trunk links, something we will need to change in future projects. The next part of the section will detail how we set up our aggregated links using an Ether channel protocol. In our network, we used Ether channels everywhere in order to increase the bandwidth we have going to certain areas of our network, such as our core switch. The Link Aggregation Control Protocol will allow us to combine two or more physical links on a switch to function as one logical interface. If we examine the connections going to our distribution switches to the core, we combine 4 fast Ethernet links together to create a single port group on each switch, then set up an Ether channel to create a new logical interface that is capable of handling aggregated bandwidth up to 400 megabits per second, as we mentioned earlier in this video. If we look at the running configuration for our core switch, we can see that each interface a part of the Ether channel is set to being in the trunking mode, as well as having its channel protocol set to LACP, as that is the Ether channel protocol we are using, and that's a member of the same channel group. If we examine the Ether channel summary of both devices connected via an Ether channel, which in this case is our core and distribution switch, we can see whether they are working or not. Not only can we see the interfaces that are a part of the Ether channel, but we can also see which flags are present within the channel as well. The S and the U flags have been set, where the U flag indicates that the channel is in use, and the S flag denotes that it's functioning over layer 2. In the final part of this section, we will explain how we implemented the spanning tree protocol into our network. This will allow us to prevent any switching loops from occurring within the network by negotiating a loop-free path that all leads towards better efficiency in the network. Switches in our network send bridge protocol data units called BPDUs out every port to see if any adjacent switches have a bridge ID lower than its own, a value made up of the switch's STP priority value and the MAC address. The switch with the lowest bridge ID is elected as the root switch, which will function as a reference point for all data communications in the switched network. In our case, we set our layer 3 switch 1 to be the root bridge, as we had set it to have the lowest bridge priority value in the network, with the other distribution switch having the second lowest bridge ID, so it could function as the root bridge in case the original one has crashed. Each switch in the network will then calculate which interfaces need to be in a forwarding or a blocking state based on their distance from the root switch. If the port is a root port, denoted with the letter R on screen, which means that it has the lowest cost of the root bridge and can forward/receive packets, while designated ports, denoted with the letter D on screen, functions as a port that is also capable of accepting and forwarding packets similar to a root port. Lastly, we have blocked ports, which are represented with the letter B on screen, which are not capable of receiving or sending any packets on that port, but instead are only capable of accepting BPDUs from other switches. We can check our spanning tree information on our switch by running the command show spanning tree. It will separate the information into different areas based on VLAN information, as we are utilizing the Cisco proprietary per VLAN spanning tree protocol. We can see the spanning tree information for the root bridge, which contains information such as the priority value for the switch, as well as the lowest cost to reach the switch. Below this information, we will find the local spanning tree information, which will show the local bridge priority for the switch, as well as the states of each one of its interfaces if it's either in a forwarding or a blocking state. If we run this command on the root bridge, the information shown in the root and bridge ID will be the exact same, and we will also have a message that says that this switch is in fact the root bridge. All of the interfaces on a root switch will be labeled as a designated forwarding state. If we run the show spanning tree brief command, we can see the bridge priorities values are set for each VLAN. This way, we can specify switches to be the root bridges for specific VLANs. All unconfigured VLANs will have a default priority value of 32,768. With spanning tree, we do not want any client devices to submit false BPDUs onto the switch network, so we will need to configure BPDU filters and guards on every access port. BPDU filters prevent the sending and receiving of BPDUs on an interface, while BPDU guard shuts down a port if it does detect a BPDU incoming from an end device. The last thing we configured on our spanning tree network was to enable the spanning tree portfast command on all the access interfaces going to our end devices. By enabling portfast, we can configure a switch to allow those devices to connect to the network nearly immediately without having to wait for the port to transition from a listening/learning state to a forwarding state. This greatly increases the spanning tree convergence time on our network and greatly cuts down on the time it takes for devices to communicate on the network. For the second section of this video, we will be discussing how an Ether channel is capable of load balancing across an aggregated link. Originally, we assumed that an Ether channel load balances data traffic by distributing the fragmented traffic equally across all the links that are a part of the Ether channel in sort of a round-robin manner. Based on the load balancing configuration we used, we got some different results than what we expected. The method of load balancing that we used uses the source IP and the destination IP as variables in order to determine which interface of the port channel or ether channel that it will use to transmit the traffic. As you can see on screen, while we check the IPs of all the different switches within our network, we can see that the traffic going to each one will instead choose a different interface on the port channel. Our core switch has the IP of 192.168.10.15, and it is going through the process of checking which ports the traffic it sends will take in order to reach the other switches within the network. This actually makes a lot of sense, as now we don't have to fragment the packet across 4 different links, and instead we'll just use one dedicated link depending on the destination IP we are sending to. Though it is not what we expected, this is still a very efficient way to load balance the traffic over the network in a way that will create no congestion over any of the links on the switch. Instead of using source and destination IPs, you can also load balance based off the source and destination MAC addresses for all the devices in the network, but for this lab, we felt that using IP addresses would be much easier. In the last section of our video, we will be demonstrating how we introduced an issue into our network, the effects it caused, and how we diagnosed and resolved the problem later on. The problem we chose to introduce into the network is a simple one, where it is basically a misconfiguration of the port group on the distribution switch that goes to one of our layer 2 switches, where rather than it being set up for trunking, it has been set to function in access mode, which will then throw off our ether channel, our VLAN traffic, and change the spanning tree topology. Let's look at switch 5 before we introduce the problem. We should note that its current cost of the root bridge has been set to 12, and it's current that port group 1 is set up to be our root port to the root bridge, which is directly connected to the interface that we are about to misconfigure on that root bridge. To perform the misconfiguration, all you need to do is enter the port channel interface on the root bridge, in this case port channel 4, and simply put the command switch port mode access to flip it into access mode. Now let's see how this affects the spanning tree information back on the layer 2 switch. Port channel 2 is now listed as the root port, while port channel 1, despite it being directly connected to the switch, is now placed as a designated port, meaning it does not have the shortest cost to the root bridge. Speaking of root bridge cost, we can now see that the cost to reach the root bridge from the layer 2 switch has now been set to a value of 15. If we watch the command line interface on switch 5 when the problem was introduced, we can see that it does report multiple errors on ports 11 and 12, the interfaces that were used for the ether channel, reporting that there has been a native VLAN mismatch, as well as port channel 1 being put into the down state. Thankfully, to fix this issue caused by the misconfiguration is really easy. All we need to do is go back into the port channel on the root bridge and change it back from going from switch port mode access back to switch port mode trunk, which will then fix all of the ether channels and spanning tree information in the network. If we go back and check the spanning tree information on the layer 2 switch, we can now see that all the information has returned to the way it was before, where the root cost to get to the root bridge has been set to the value of 12, and that port channel 1 is our root port in order to connect to the root bridge. Also, you can see on the left hand side, we are now capable of pinging our default gateway, which was also the root bridge, so it seems like we were able to fix our problem. This concludes our video for the lab. We'd like to thank you for watching the video, and we also hope that you've maybe learned a thing or two about switch network infrastructure, or even anything regarding the networking protocols we discussed. Until then, we will see you next time.